we're now going to revisit systems of pulleys, but then we're going to recognize that the pulley here actually has a mass. So we'll give this a little bit of an M here. Okay, and therefore it will have moment of inertia. So how does that actually change the question here? Well, we do have force gravity going downwards on this. And upwards on this is going to be force tension 1. Okay, this one, we will have force tension 2 acting on it. And then we'll have force gravity X opposing it. And force friction opposing it. Now they both will accelerate together. The force tension 1 and 2 are not going to be equal to each other this time because of the presence of this mass here that exists in the pulley. Okay, so how do we handle that? Well, I'm only going to go through this generally. So what this means is the observed acceleration of these two objects is going to be less than what we would think, okay, if we do not include the mass of this pulley. So now that the mass of this pulley is included, acceleration of the system will be less. So what's it really going to look like? Well, from the perspective of the pulley, I just do like a circle here. We're going to have a force tension 1 pulling it this way. Now we're going to have a force tension 2 pulling it this way. So essentially there's going to be 2 different torques. And of course we've got a radius in both cases here. Okay. So the addition thing is we're going to have a third equation here. So the force net on this part right here, if we consider this direction as being positive, so we'll have force net is equal to force gravity minus force tension 1. For ρ here, I'll do it down here, we're going to have force net is equal to force tension 2 minus force gravity X minus force of friction. For the pulley, we're going to have a system of torques here. So we're going to say then that the torque net on this is going to be equal to, now this direction we called positive, so that would be force tension 1R minus force tension 2R. Okay, and those are our equations. So we'll have 3 separate equations, and it is a systems of equations in order to solve for it, because we have 3 variables that are not known when we do this. So that's how that would change. You know, again, we're just looking at this conceptually, so I'm not going to go through all that mathematics that is involved with that. Our next situation here is, what if I have a bucket wound around, okay, some type of a cylinder, and there's a bunch of rope there, and this thing is accelerating downwards. So, you know, what's different about this? So if we consider that this, again, has a mass, we'll just give it, of course, it's given a 0.8 kilograms here. So straight downwards is force gravity. Upwards is force tension. So the net force equation on this, so force net, is going to equal, now if we call, you know, going this way again positive, it would then be force gravity, you know, minus force tension. Now again, for the perspective of this pulley here, we have our radius R here. We're going to have the torque net on that is equal to, it's going to feel force tension pulling downwards on it this way. Think Newton's third law. So it'd be force tension multiplied by the radius. So there's our 2 systems of equations there. And what would this look like? So we're going to have I times alpha is equal to force tension times R. Now we have a bunch of unknown variables here, but we can substitute something in for this that will help us only have a couple of variables. But this, of course, is going to be MA equals force gravity minus force tension. Now let's call this the bucket B and this the pulley P. So I'm going to put a sub B right here, because this is the mass of the bucket times A equals force gravity minus force tension. Okay, now up here, How can we get rid of this alpha? Well, remember, acceleration does equal r alpha. Okay, so alpha is equal to a divided by r. Okay, so I'll have I, a divided by r is equal to force tension r. Okay, and then we can plug in for moment of inertia because this is going to look like a disk. So I is equal to 1/2 mr squared. Okay, so we can put 1/2 mr squared for that. We have our radius value. We're just solving for a. We can use the systems of two equations here. We have this equation here. I'll put a check mark by it. In this equation here, we can solve for acceleration and then go backwards and find tension force. Because again, we have two unknowns. Unknown would be force tension in both equations and acceleration in both equations. So that's how, if the pulleys actually have mass to them, you account for the fact that there's a torque on them and that there indeed is moment of inertia. And again, this will accelerate less than gravity acceleration because the pulley now has mass. And last but not least, what if I have a bowling ball and it rolls down a hill like this, or it rolls down an incline? We can use an energy system of doing this. So if it starts at rest, initially we have gravitational potential energy. There's no kinetic, there's no springs attached, and there's no work done. At the bottom, of course, it's going to be rolling, but also moving. So we're going to have kinetic energy translational, put the letter T there, plus kinetic energy rotational. So at the bottom of this incline, it's going to be spinning, so therefore it will have rotational kinetic energy, but the center of mass will also be moving, so it has both. So what's going to happen is the linear velocity of this is going to be less than what you would expect. If you don't include rotational kinetic energy, you're going to come up with a velocity that's higher than what's expected. So how we deal with this, we're going to go mgh equals 1/2 mv squared plus 1/2 I omega squared. Okay. Now I, of course, we can sub something in, but what about the W? Well, remember V is equal to R omega. So omega is equal to V divided by R. So I can sub that. I see the W there. I'll do that. So we have mgh equals 1/2 mv squared plus 1/2 I times V squared over R squared. If I substitute that in there. And then all you got to do is substitute the I in for that. And then the only unknown you'll have is a velocity, because you'll know the radius, okay, of the bowling ball or whatever object that's moving in there. And there's a simpler equation. Lots of things will cross off when you do this equation, but that's the general gist of it. So the important thing is that you realize that the ball, when it gets to the bottom, is going to have two kinds of energies. And if you don't include this in your calculation, V is going to be higher than what it should be. Okay, and that's it for rotational dynamics.